One of my goals with this course on practical geology is to have you actually observe geology and interpret the geologic world around you. To get you out in the field, there are two types of fieldwork you can begin right away, and the choice, it's entirely yours. The first type of fieldwork is what we discussed last time. That's where you are hiking around, getting a feel for landforms of a particular landscape, and figuring out what the landscape is telling you about the geology. The second type of fieldwork is all about going directly to a specific place. My recommendation is that you go to an outcrop, a place where rocks have been exposed. You might have learned about an outcrop from previously hiking around or from your reading. The rocks might be exposed due to a road cut or mining operations, or the rocks might have been exposed by erosion, whether by a river, a glacier, or waves. Even strong winds in places like the Badlands can erode away surrounding material to leave an outcrop. So for this lecture, I thought I would share skills that will give you more confidence and maybe some inspiration to get you outside and look around at things more closely for yourself. Collecting is one great way to get started. You can collect rocks with interesting features, or minerals, or fossils. All are a lot of fun to collect, and whenever you're collecting, you're learning not only the geology of whatever it is you're collecting, but also some of the other rocks you're looking at along the way. Where can you collect and take samples? It turns out that there are a lot of places. Exposures along roadsides, unless signage indicates otherwise, are fair game. Most riverbanks are also. The public is allowed access within a certain number of feet to water and roadways. Many parks and public lands will allow collecting, but you should always ask. Really, the big no-no is private land. But even if you never do any collecting, getting out to hike and maybe taking photographs is a great way to get yourself thinking about geology of where you live and places you visit. In a way, it's like studying the history of your hometown. Geology will help you see how the present landscape came about by looking at its geologic history. I also want you to realize that doing field geology is doing science. This is something that even a lot of scientists don't get. Some laboratory scientists even question the significance of fieldwork. After all, lab, instrumentation, computers, and advanced analytics have changed the science of geology for the better. Is field geology really generating significant data? The answer is yes. Geology, especially practical applied geology, has always been a field science, and it always will be. I can't emphasize enough how valuable fieldwork is. Sure, fieldwork is a great way to get out and observe geology firsthand, but what you will be doing is also the fundamental component of geological science. The geologic maps that you see and the geologic theories that you'll hear about all began with observations in the field. So even if you're telling yourself this is just for fun, I want you to keep track of what you're seeing and where you're seeing it. Somewhere down the line, you or another geologist might just use the data you record. And really, always bring a camera so you can at least walk away with a picture. Doing fieldwork is a lot about preparation. In fact, the primary thing that separates successful observing from just being outdoors is being better prepared. You can prepare to be safe, prepare to be comfortable, and prepare to understand more of what you're seeing. Your aim should be to come away from any given day in the field safely and in good spirits. If you didn't enjoy fieldwork, you'll be hesitant to do it again. If you get hurt or if you don't feel comfortable in certain situations, you'll be missing the fun of field geology. Admittedly, I enjoy visiting a place for the first time and trying to figure out the geology, just from observation that I make. But the more you know ahead of time, the better off you'll be. I mentioned geologic maps. These are maps of the location and distribution of rocks in any area. Like any map, you can get paper copies, but there are also maps you can download to your cell phone. I recommend a free open-source app called Rocked. It's funded by NSF and released in 2016 by the University of Wisconsin geologists. The desktop version of the same project is called MacroStrat. Both amateur and professional geologists enjoy using these. You can look at a large-scale feature, but also zoom in, and you can point to any given region to get more information. For example, you might notice all the pink regions in much of Minnesota, and you click into those areas to read that its bedrock layers 2 to 3 billion years old. But going just a little bit west into the Dakotas, there's a big green region, and you can read that the bedrock layer there is far newer, at only 100 million years old. Such apps make it very easy to learn something about the geology of wherever you're planning to visit. There are also geology guidebooks that actually describe the geology of road cuts, outcrops, or overlooks. But a word of advice: you can buy used copies of these types of books fairly inexpensively, but if the book is older than about 15 years, you might want to get a newer version. You also need information that will help you stay located. That's important. The USGS has topographic maps of the entire U.S. online on their National Map Viewer. They provide a wealth of information about topography, trails, roads, and park and state forest boundaries. Also, look at the website for the Geologic Survey Office run by your state government for local geologic information. Individual states have a lot of very practical info that goes beyond what's available from the USGS. When I go into the field, I use old-fashioned topographic maps. These are available at outdoor stores. When I'm in the field, I put notes on them about interesting features or sample locations. You should also have a GPS device or a compass to help keep you oriented. Google Maps can be really great for keeping you aware of where you are, if you can maintain access to it in the field. In addition to showing the lay of the land and locations, you may not realize that Google Maps is also great for finding outcrops and road cuts. The satellite imagery allows you to see exposed bedrock and landforms. Especially with low vegetation, rock exposures are easy to spot. A cell phone is really a must for safety, and having maps and downloaded maps at your fingertips is really amazing. Investing in a sturdy waterproof case for your phone will cost much less than replacing that phone. But there is no cell phone coverage in a lot of places, so you should always let people know where you're going to be and roughly when you can be expected back. Since you're going to be outdoors, you'll want good shoes. You need ankle support and shoes with good tread and shoes that are comfortable. Cheap soles can be both slippery and too rigid, which is hard on your feet. You'll want a hat. You'll also want sunblock, mosquito spray. Rain gear is a life or death must in the mountains where the risk of hypothermia is very real. Even to prevent getting wet in a pop-up rainstorm, if you're not comfortable, you're not going to enjoy the fieldwork. Also, dehydration hits you long before you're fully aware of it. I remind students on a regular basis to drink and to eat something, even though they're not hungry or thirsty. You might even set a timer on your watch to make sure that not too much time is slipping away between rehydration stops. There is also geology gear. This is the stuff that you need to make sure that you will be able to complete a successful field day and your observations and collections serve a purpose. The fundamental component of scientific observation is a good field book for recording your own notes. Plus, you need good pens and pencils. Make sure you write things down and write neatly so you'll be able to read it tomorrow. Good field books are water resistant or water repellent and rugged enough to withstand abuse. A good field book can be worth far more than the $8, $10, or $12 you're going to spend on it. A hand lens is very helpful. A hand lens is a small magnifying glass that you can carry easily. You hold it a couple inches away from the sample. This allows you to see quickly what the minerals and textures of the rock are. If you plan on collecting anything, you'll need sample bags that are sturdy enough and easily labeled. Plastic is fine unless moisture might lead to mold, and then cotton becomes better. For a surface that hasn't yet turned into rock, a trenching tool can be used, or a pick if it's more compacted, to clear off an outcrop or clear away overburden. You should also think about investing in a basic 2-pound rock hammer. Estwing is one of the several manufacturers that make good quality rock hammers for 25 bucks or 30 bucks. Whatever model you get, make sure it is all a single piece. In the old days, before my time, the head was metal, but the handle was wood. Having the head come off upon impacting a rock was really unsafe. A rock hammer is really the geologist's go-to tool. Rock hammers come in two forms. For sedimentary rocks, it's good to use a chisel tip. This allows you to split sedimentary layers open. For pretty much everything else, use a pick tip. So this makes a good first rock hammer for beginners. This allows you to focus force on a small location. Both types have a flathead hammer on the opposite side, and really both will work fairly well on all types of rocks. Rock hammers are a great tool, but they are also the cause of many rookie injuries. A brand new hammer will send off shrapnel if you hit it against a very hard rock. You should always wear eye protection. Safety glasses, safety goggles, or safe glasses. Now let's talk more about what to do in the field. If the outcrop you're heading to is a road cut, make sure that you look for signage that indicates whether or not you're allowed to park your car on the road. Some state highway laws prevent stopping along the roadside for anything but an emergency. If you are allowed to stop on the roadside, make sure your car is pulled way over to the side. At many road cuts, traffic is the biggest threat to your well-being. Please be careful. But you also don't want to park directly in front of the outcrop. If a rock comes tumbling down, you get a dent in the side of your car as a souvenir. It's happened to me. Ouch! I lost track of where I was on the outcrop, and I ended up being very high up and directly above my pickup. When I dislodged a boulder, I was looking down and the boulder went, and I got a little extra customizing on that vehicle. I always tell students to learn to get comfortable at an outcrop. Although you may be at the outcrop to collect a specific fossil or mineral, still, you want to take your time and take in everything. You should be looking not just at the rocks, but the slope of the exposure and the vegetation as well. Remember, you're outside. You're doing something that's kind of unique, and an opportunity for discovery awaits. Enjoy it. As you approach the outcrop, there are a couple of important safety observations that you should go through. The first is how steep the exposure face is. Cliffs can be dangerous both because of the challenges to access. Doing geology at a cliff face or on top of a cliff is not a good idea, and because of the dangers of falling rock. Look at the ground in front of the outcrop. Are there rocks that have fallen from above? If so, you should scan that outcrop for boulders that might fall soon. You'll have to be careful that your footing is secure while you're working your way around the outcrop. You do this by slowly adding weight to your front foot to feel if the slope is stable. Don't just step and assume your weight will be supported. This is especially true on wet or icy surfaces. I've had many an early spring pre-melt tumble down snow-covered mountain drainages. If you're looking at sand or gravel or other unconsolidated deposits, note the slope of the exposure. I want to show you something called the angle of repose. This is the angle at which all unconsolidated deposits are stable relative to the horizontal. You can observe this with any granular material. In the kitchen, it can be sugar or coffee beans. Let me pour some salt for you. Can you see the angle of the slope? The same thing occurs in the backyard where it can be playground gravel or sandbox sand. Here is fine sand. For sand or gravel exposed in outcrops, the angle of repose is between 25 and 30 degrees. If you try to make a pile steeper, it just collapses. Remember, in any granular material, when moisture prevents grain movement, you can temporarily get a slope that is steeper than that angle of repose. Here you can see me pointing to an over-steepened exposure. You should not get as close as I am. Getting caught in collapsing sand or gravel, or even a grain pile collapse, is dangerous. It's best just to walk away from steep slopes of unconsolidated material. So, the outcrop you are looking at should seem reasonably approachable, without a lot of collapsing material. And you should have legal access to it. Now let's take a look at the rocks. Now, it's actually quite rare that you can identify a rock that has an old, weathered surface. The main exceptions are volcanic glasses like obsidian, or in some cases, petrified wood. Both are hard and both made of really small constituents. So the first thing you have to do is find a fresh surface. That is, a surface of rock that has not been weathered. Sometimes you can find a fresh surface on the outcrop where a rock has broken off recently. You can also find a fresh surface on rocks that are lying at the base of the outcrop. After all, they have broken off. But if you can't find a fresh surface, it's time to use your rock hammer. A basic identification of igneous, sedimentary, or metamorphic rock will get you on your way. Igneous rocks crystallize from a liquid, so the component crystals will be interlocking. Sedimentary rocks are frequently an aggregate of grains with a cement between the grains. In this conglomerate, you can see the individual particles. In metamorphic rocks, you will often see a pattern, like in this gneiss. The identification process in the field sometimes can be tricky. One of the things you learn very quickly is that there are not many outcrops and exposures that look like textbook pictures. Real-life rock exposures can be complicated. Selecting where to hammer off a sample is learned with repetition. I pick one of the fallen rocks or a face of the outcrop that you can physically break off. You're looking for a rock that is small enough to break off and large enough to allow you to identify the rock. A large boulder or a large flat face of an outcrop is not going anywhere. Don't start hammering away on something that's too big to break. This is a very breakable size of rock. We're starting small. We're making sure that the rock we're hammering is stable. We're going to use the blunt end of the hammer, and we're going to wear glasses for safety. Now it's just a matter of taking a swing. It takes practice, but you will get it. Some people get really good at breaking the edges off a rock with just a rock hammer. That's called trimming a rock, and it's great to have that skill. So now you've broken off a piece of the rock you're looking at. What does the fresh exposure look like? There's some basic things to observe that can be done with a minimal amount of training. First, describe color. This one has grays. This one has grays and blue colors in it. This one is tan and brown. This one just plain black. Be evocative with your descriptions. For example, the color we just called blue, you might describe as periwinkle. Great. Now, look at the components of the rock. This one is made up of sedimentary particles. It's shale. This one has minerals. In this one, the individual components of the rock are too small to identify. That happens. You can't always tell what a rock is composed of in the field. On a regular basis, I have people show me rocks that are too weathered to identify. The color and the form of a weathered rock can indeed be interesting, but I can't tell them what the rock is. When I ask if I can break the rock, there's always a pause to decide. Break it and learn what it is, or leave it and enjoy the rock as found. Sometimes that's a tough decision. When kids have collected something, I usually don't even ask. I just tell them I don't know what it is, and I'm happy they're enjoying geology, and I'll just leave it at that. If you can tell what the components are, look at them closely. Look for any patterns. This one has alignments. The elongate minerals have a trend. This one has layers in it. Finally, notice whether the rock breaks easily. Does it fall to pieces or crumble readily? All of these are observations that you can do. In the process of writing down your observations, try to compare what you are seeing with the type of rock you expected to find, based on your preliminary reading and research. Once you've looked at the small-scale geology of the exposure and have given some thought to the rocks and features you're seeing, it's time to step back. Describe the outcrop as a whole. Look for patterns. This one has strata. This one has deformed rocks. This one has fractures. In many ways, describing an outcrop is about describing lines. That's why one of the most important things you can do at an outcrop is to draw it. Not just take a photograph, draw it. Simply looking at something isn't the same as understanding what you're seeing. So taking a little time to improve how you draw can help you see more in the field. It's not the finished picture that's the most important thing. It's the process of learning to see characteristics, and drawing helps you see them. When using a field book, there are a couple conventions everyone is supposed to follow. Always record the date and time when you're at a field location. You should also describe weather and general conditions. Are you looking at a road cut? You also should write down anything that's unique about the location. Weird vegetation, a unique roadside, something strange that happened to you while you were at the outcrop. These will help remind you, a memory trigger, of the place and time you did the fieldwork. For example, I was with a class at an outcrop where I was going to give a quick field lecture on rock magnetism and the orientation of magnetic minerals in an igneous rock. To demonstrate the mineral orientation, I asked the student if I could borrow her Nalgene plastic water bottle. It was longer than it was wide, so it would be a good teaching tool for the alignment of minerals. It was only after she tossed it to me that she remembered that the lid wasn't screwed on. I got wet, students laughed, and without any prompting, they all entered the memory in their field books. When they go back and read those notes, they may laugh again, but they'll also remember that outcrop. The point is, you should always use your field book as a vehicle to develop your thought processes. Beginning geologists get to an outcrop, take a look around, break up a couple rocks, but then can't figure out the next step. Writing in a field book will give you an opportunity to think about things, collect your thoughts, air your concerns and questions, and preserve your interpretations. If you do find fossils or minerals or a rock type that you're interested in collecting, stop for a second. It might be easier to collect samples from the rocks that have been broken off the outcrop and collected at the base. Those rocks tend to be smaller and may be easier to trim. It may be that some fossils or minerals have weathered out of the outcrop, and you can find them loose at the base of the slope. This is by far the best way to collect samples. Conversely, if the only place you're seeing a fossil or mineral is embedded in the bedrock, it's probably best to take a picture and leave it until you're more experienced or can get help. Especially when you're just beginning, it's more likely that you'll just destroy whatever it is you've observed. Let's go back to my steel plate for a demonstration. This is a rock from Minnesota. It's just loaded with brachiopods. Let me try and get one out. Ouch! Instead of getting the brachiopods out, I've broken them. Now let me show you something. Now these are from the same spot. They were weathered out of the outcrop, and I found them on the slopes. It's much easier to collect them this way. Make time to label your sample or photographs as you go along. Put the date and the number in the sequence of the sample you're taking that day. Put the same information on your specimen bag and in your field book. Mark on your outcrop drawing where you took the sample from. Write a description of the specimen and note why you wanted it. Was it a unique rock type? Did it contain interesting minerals? Did you want to show it to someone? Write things down. When you later pull it out of the drawer, you'll be pleased how much information you already gathered. You'll be able to remember what you learned and even do more research on it if you want. The important thing I want you to realize here is that the landscape will provide clues as to what types of rocks are in the area. Resistant rocks will form hills. Non-resistant rocks will form valleys. Rivers erode the channel that they occupy, and frequently the location of that channel is influenced by an easily eroded rock type or a fault or some other geology that you can see. Landforms can provide clues to the history of surface processes that have influenced the region. Glaciers, rivers, and wind all leave distinctive landforms. Also, keep an eye on vegetation. The underlying soil is influenced by rock type, and resulting soil, in turn, influences what vegetation will flourish or not flourish, as the case may be. One last thing I encourage you to do. When the day in the field is done, take some time to reflect about your day in the field and record those reflections in your field book. Write about what you saw, what you learned, and maybe what you'll do next time out. Also, write about your experience. What parts did you enjoy? What might you do next time to improve your time in the field? Time and time again, folks referred to as amateur geologists make an important find. For example, 2 of my students were out looking for new and interesting geologic exposures. Most of the time, this involves exploring road cuts, but this time they found a drainage ditch being excavated. It turns out that exposed in the ditch were lake sediments deposited in Glacial Lake Benson, a lake that formed at the ice sheet margin as it retreated from western Minnesota. This type of sediment, with alternating layers of summer and winter deposits, had never been found before in association with Lake Benson. That site changed the interpretation of both the characteristics and significance of that lake. In fact, one of those students and I are still studying that lake 15 years later. She's now a professor at Utah State University. Adding to the body of science is a wonderful reward in and of itself. Different people will approach fieldwork for different reasons. Some learn about nearby landscapes. Some focus on geology when traveling. Understanding the geology of a park or preserve can be like understanding the brushstrokes and shading that go into a masterpiece painting. Some collect, and others just use the time to unwind or try something different. All of those are great. Field geology is a great way to learn and appreciate what geologists have learned about the history and wonders of our amazing planet. Try it. I think you'll like it.